This video is on section 5.1 notes, random variables and probability distributions. A random variable usually denoted by x is a variable that has a single numerical value that is determined by chance for each trial. These variables can either be discrete or continuous. And I know that definition is a little bit abstract, but we'll see examples of that in a second. So in case you have forgotten the difference between discrete and continuous, discrete values are finite or countable. A lot of times I think of them as whole numbers. They don't have to be whole numbers, but a lot of times they are. A continuous number has infinitely many values, and the values are not countable. And I often think of these as being decimals, but they're values where you can add more and more precision if required. And so we're gonna apply these words to different random variable examples here, just so we can see the difference between discrete and continuous, but also so we can see what some random variables might look like in an actual setting. So here it says the number of overdue accounts in a department store at a particular time. Would that be a discrete random variable or a continuous random variable? And the answer is discrete. You wouldn't have part of an overdue account. You either have one or you don't. So that would be a discrete number. The number of deer killed per year in a state wildlife preserve, this would also be discrete. You're not going to have half of a dead deer. It's either a whole number or not. Tensile breaking strength of a steel cable. So this would be like the force that a steel cable could have before it snaps. And this would be measured in maybe like pounds per square inch, or I don't know, somebody tell me who has more knowledge about this. But because this is something where you're talking about weight or you're talking about force, you can always add some more precision. So if they said that steel cable could hold 4,000 pounds, well, it'd be like, well, is that an estimate, or was it literally only 4,000 pounds? And the answer here would be, well, maybe it was 4,000 pounds, but some ounces. So there could be more precision to it, maybe 4,000 point something pounds. And so this would be a continuous measurement, because in terms of forces or weights that can be held by cables, you're probably going to be able to add some more precision to that measurement. And so that's what would make it continuous. And the precision could be in the form of decimal places, or could also be in the term of units that are more precise. Your blood pressure, if you've gone to the doctor anytime recently and they've taken your blood pressure, those are not measured in decimals. There's not more precision there. They're measured in two integer values and two whole number values. And so this would be a discrete measurement. Increase in the life attained by a cancer patient as a result of surgery. This would be a continuous random variable, continuous, because if you said, oh, they lived this many months, odds are it wasn't exactly at the 30-day or 31-day mark. It was probably months and some weeks and some days, and they just rounded to the nearest month. You could always say, well, give me more precision. So how many weeks was it? How many days was it? How many hours in that day was it? How many minutes? So with time, anytime you have time, it's always a continuous measurement, because you can get more and more precise. Right, so these are all examples of random variables, meaning they're just different things that we can measure, and they're things that we're measuring with numbers. All right, next we have a probability distribution. Is a description that gives the probability for each value of the random variable. So you'd say like the probability, if we had number of deer killed per year in a state wildlife preserve, maybe the X values were like 20, 25, something like that. And so then you'd say the probability that 20 deer were killed, the probability that 25 deer were killed. So that's what they're talking about. So it is often expressed in the format of a formula, table, or graph that gives possible values of x and the probability p of x associated with each value. We're typically going to work with tables and graphs. So here's an example. It says, assume that male births and female births are equally likely. I actually learned from the textbook that male births are more likely. I guess that makes sense based on different cultures, but male births are have a probability of 0.512 instead of just 0.5. But assuming that they're equally likely, because there's only two options, male versus female for births. So let X be the number of females when two babies are born, fill in the table of the probability distribution, and then draw a probability histogram. Okay, so what we're going to do first to fill this in, where X is the number of females and two births, is we have to figure out what all of our options are if there are two babies born in a row. And which ones give us two females. So we could have male, male, we could have male, then female, we could have female, then male, and we could have female, then female. So when babies are born, those are all the different options we could have. So what's the probability that 0 females are born? And that would be, we have 4 options, that would be 1 out of 4. Or a probability of 0.25. The probability that 1 female is born would be these two options, so that would be 2 out of 4, or a 0.5 probability. And then the probability that 2 females are born is 1 out of 4, or a 0.25 probability. Okay, and then it says to draw a probability histogram. So for 0 females born, that was 0.25. So right up here. And then 1 female born is 0.5. It goes all the way up. And 2 females born is 0.25 again. Okay, there's our histogram. Right. So now we want to look at probability distributions specifically from discrete random variables. So we're looking at random variables that are probably going to be whole numbers, but are at least things that we could count. So not decimals in between, but just solid numbers from one to the next. So we're going to look at 2 different things that we can calculate, well 3 really. The first is expected value. So it says let X be a discrete random variable, which we already talked about, with a probability distribution, probability of X. The expected value is denoted by E of X and can be found using this formula. And this is just the formula for mu. And if you recall, we had kind of calculated this before, but we didn't really use mu because we were never talking about the population. So here we're going to be talking about the population, but this is what we were doing for the sample statistics, and we were talking about X bar. This is the mean. So what they're asking us to do is find the sum of all of the pieces of data, which is what we did with the mean, right? We would take the sum of all the pieces of data, and normally we would divide it by the number of pieces of data that we had. But instead of doing that, to find the mean piece of data, or the measure of center, right? The measure that would kind of, or an expected value is the wording we're using that could kind of represent the data. We're going to take the summation of each individual data point multiplied by the probability that that data point shows up, which gives us a weighted mean instead of the calculated mean. So it's the value that you would expect to observe on average. I know we don't use average, but it's the value that you would expect to observe if the experiment was repeated over and over. That's what the expected value is. All right, then we have the variance and standard deviation, because those are very closely related. So we have this lowercase sigma And if you recall, sigma squared is the variance and sigma is the standard deviation. So here we're using the random variable minus the mean squared times the probability. And we're going to go ahead and calculate those using this same example that we had before. So it says to compute the expected value, standard deviation, and variance for the two babies. Okay, so here we're going to calculate the expected value. I'm just going to write that above the table since it has the formula instead of what it represents. So this is going to be 0 times 0.25, which is 0. This one is going to be 1 times 0.5, which is 0.5, and this one is 2 times 0.25, which is also 0.5. All right, and so we've calculated each of these individual values, and then it says to find the expected value or to find the mean, we just add those values up, we sum them. So add them up and I get 1.00. So that's the value of mu. Okay, now over here to calculate the variance, we're going to find each of these and then we're going to sum those as well. So I'm going to do x minus mu squared times the probability. So that's 1 times 0.25. The only reason I'm doing these not on a calculator right now is because this table is pretty nice. The values are not too bad. Otherwise, I would be using a calculator. So that's 0, which is going to zero out the whole thing since they're multiplied. And this is 1. 1 times 0.25 is 0.25. So sum those up, we get 0.5, and that is the variance or sigma squared. And then for sigma, I get 0.7. So just a reminder so you can remember what these values mean or what their importance is. The expected value is a measure of center that tells you where your data is. And then over here, the variance, the standard deviation, tells you how spread out your data is. It tells you how much your data varies. So because of this, since there's a mean of 1, we would expect to get a mean of 1 female and 2 births. And that fits. That's kind of, you know, what we had for 50% or for 0.5 probability of our data. All right, here's the next example. It says, suppose a random variable x, and they didn't tell you what it was. Just some, it could have been any of those things from before. We talked about the deer, we talked about blood pressure, that'll probably be a different number. We talked about overdue accounts in a department store, so it could have been any of those. But it says, suppose a random variable x has the following probability distribution. So the first thing they want us to do is find the probability that the random variable is 4 because that value is missing. So we know that the probability of all of these has to equal 1. And the reason for that is because this represents all of the data. And so if we calculate all of the data all together, that must be 100% of the data. And to do the probabilities as percentages, or the percentages of probabilities rather, that would mean that all of these have to add up to 1, or they all have to add up to 100%. So what I'm going to do is I'm going to say 100% of these, or 1, subtract off 10%, subtract off 30%, subtract off 40%. I'm going to do 100%, subtract off all of those to get my probability. But I'm not going to do it in percentages because probabilities are supposed to be decimals, not percents. So I'm going to say 1 minus the rest of these will give me my missing probability. Okay, so the missing probability is 0.05. Okay, construct a probability histogram. So since the highest probability is 0.4, I only did 4 lines. And then these across the x-axis are going to represent my random variable x. So for x is 0, the probability is 0.1. For 1, it's 0.3. For 2, it's 0.4. For 3, it's 0.1 again. And then for 4 and 5, those are both 0.05. Okay, now it says to, I'm gonna try to make it so both of these can be seen. It says to find mu, sigma squared, and sigma. And so I'm going to write down my x values, my p of x values, and then to find mu, I need to do x times p of x and add them all up. So it would be 0 times 0.10, 1 times 0.3, 2 times 0.4, 3 times 0.10, 4 times 0.05, 5 times 0.05. Okay, so mu is 1.85. Okay, and then next I need to calculate my sigma squared, and so that's going to be x minus mu squared times p of x. So I have 0 minus 1.85 squared times 0.10, 1 minus 1.85 squared times 0.30, 2 minus 1.85 squared times 0.40, 3 minus 1.85 squared times 0.10, 4 minus 1.85 squared times 0.05, and 5 minus 1.85 squared times 0.05. Just want to make sure I didn't have a typo in there. 3 and 0.1, 2 and 0.4, 1.3. And for all of these, before I say my final answers, I'm only going to use one decimal place. Because for measures of center and then measures of variation, we only do one more decimal place than the numbers that we were using from our data. So we had used 0, 1, 2, 3, 4, 5. Those were whole numbers. So I'm just going to round to one decimal place. Okay. Next it says locate the interval mu plus or minus 2 sigma, and we haven't seen it written with Greek letters, but we have seen this written with the letters, the variables that we use to represent the sample statistics. So there we said x bar plus or minus 2s, and this is where we're looking at the statistically typical, the usual values, the ones that are not outliers. So that's what we're going to be figuring out. We're just doing it for this case, which is why we're seeing the mu and the 2 sigma there. So mu was 1.9 plus or minus 2 times the standard deviation. And so we have that the random variable is between negative 0.5 and 4.3 for the kind of usual values that are considered not to be outliers. So it says, what is the probability that x will fall into this interval? You might be remembering kind of your normal distribution, which is 95%. It's that second set of percentages. The first one standard deviation is 68%, 2 standard deviations is 95%. But that's not how they asked us to do it. They didn't say use the empirical rule. They said look at the x-axis on your histogram. And so when you're thinking about the histogram, then you're looking about the probability of each of these, right? So the empirical rule had percentages anyway. It didn't have probabilities, even though we know they're related. But here we can actually look at our probabilities and see the probabilities that the numbers fall in between negative 0.5 and 4.3. So I'm going to say the probability that any of the values that we get from the table falls in between these values would be 0.1 plus 0.3 plus 0.4 plus 0.1 plus 0.05 divided by the total probability or the total number of options, and that's 1. Every number that we can possibly have adds up to 1. And so the probability happens to be 0.95, not because this data is normally distributed, it's just a coincidence. Okay, so what's the probability that your values are going to fall into this interval? It's a 0.95 probability, not 95% because it's a probability, so we're going to use decimals. All right, last example says a company has 5 applicants for 2 positions, 2 women and 3 men. Suppose that the 5 applicants are equally qualified and that no preference is given for choosing either gender. Label the applicants W1, W2, M1, M2, and M3. And let X equal the number of women chosen to fill the 2 positions. So X is going to be our random variable. So first, we're going to describe the sample space, so all of our different combinations of how these 5 people could be hired for 2 positions. So woman 1 could be hired with woman 2. Woman 1 could be hired with man 1. Woman 1 could be hired with man 2. Or woman 1 could be hired with man 3. Okay, so that's everybody with woman 1. Woman 2, we already have a situation where woman 2 is with woman 1, so we're going to kind of ignore that option. Woman 2 could be with man 1. Woman 2 could be hired with man 2. Woman 2 could be hired with man 3. Okay, so now we have all the combinations where the woman could be with each other person. So now we're going to focus on the combinations that have the men with each of the remaining people. So man 1, we already have the combination where he's with woman 1 and woman 2, so we're going to look at the others. He could have been with man 2, or he could have been with man 3. All right. For man 2, we already have the combination where he's with woman 1. We already have the combination where he's with woman 2. We already have the combination where he's with man 1. So the only combination remaining is that man 2 could be with man 3. And then we have man 3 already with all the different combinations. Okay, so this is our sample space. And now we're going to write a probability distribution. So remember, probability distributions, they can be tables, they can be graphs, they can be formulas, but we're not typically going to do that in this class. And so you could graph this, but it's probably going to be easier just to have a table. So we have let X equal the number of women chosen to fill the 2 positions. We could have 0 women. We could have 1 woman. Or we could have that both of the positions were filled with women. Those are our 3 possibilities. All right, so the possibilities total 4, 3, 2, 1, 7, 8, 9. There's 10 possibilities. So the possibilities that have 0 women are 3 of them. So the probability is 3 out of 10 that no women are hired. That 1 woman is hired. 1, 2, 3, 4, 5, 6. Probability that both of the hires are women is just 1 out of 10. Okay. What is the probability of choosing at least 1 woman? So at least 1 woman means that you could have 2 women, but you have to have at least 1. So that would be 1, 2, 3, 4, 5, 6, 7. What is the probability of choosing at least 1 man? So definitely have to have 1 man, could have 2 men. 1, 2, 3, 4, 5, 6, 7, 8, 9. Are these complements of each other? And the answer is no, these are not complements. For something to be a complement, you have to think of them as opposites of each other. What is the probability of choosing at least 1 woman? The opposite of that, and I'm kind of giving away this other answer, would be what is the probability that no women were chosen? That would be the opposite. And one of the main ways that you can see it is because complements, their probabilities should add up to 1, or in this case, they should add up to 10 over 10. So if you added these, they would be 16 over 10, which means there's some overlap, right? There were the 1 woman, 1 man combo that were counted for each of these scenarios. So no, the probability of complements sums to 1, and these do not. Okay, an example of two complementary events would be the probability of at least one woman, probability of at least one woman, and the probability of 0 women. Those would be a complement. So, and you can see it right here, the probability of at least one woman is 7/10, the probability of 0 women is 3/10, and altogether that's 10/10. That's a probability of 1. That includes the entire data set.